Hey everybody, this is a video for section 14.3, as might be suggested by the title of this slide. And the big idea here is the ideal gas law, which is like the gas laws that we studied in section 14.2, a way of quantifying and calculating pressure, volume, and temperature measurements of gases. But the ideal gas law also incorporates moles, which is handy dandy if we have chemical reactions taking place and we need to do some stoichiometry. So it's a very useful equation. The other idea from this section is to compare a real gas from ideal gases. And ideal gases are the way we've been treating gases up until this point, which is a bit of a lie, as we will find out, but it's a lie that simplifies things, and we're still not really wrong when we use that simplification. Anyway, we'll see that in a few minutes. The ideal gas law relates the three things that we've already been measuring and calculating, pressure, volume, and temperature, to the number of moles of gas in a sample. And we already know that there are relationships between pressure, volume, and temperature in a gas. And the pressure-volume relationship, remember, is an indirect relationship. And so we find that the pressure and volume values are both on the same side of the equation, P times V. And we know that those two measurements, both pressure and volume, are going to be directly proportional to the temperature. So the temperature is on the other side of the equation because of that direct relationship. And now we have moles plugged in here because, like temperature, moles, which is N, number of moles in the equation, the number of moles would also be directly related to the pressure or the volume. If you have more gas in the sample, that would increase the pressure. Or if you had more gas in a sample, more molecules, and the pressure was constant, then the volume would increase. And then we have a new character in here, the ideal gas constant. And that is, as the name suggests, a constant. And the ideal gas constant is something that makes this relationship true no matter which units of pressure we might plug into the equation. And there are different values for the ideal gas constant depending on the pressure readings that we use, kilopascals or atmospheres or millimeters of mercury. And I won't ask you to memorize the ideal gas constants, the values. I'll always give those to you. But you have to make sure you use the correct one for the correct equation. Here are those ideal gas constants, the values for the ideal gas constants, and they depend on the units that we're using for pressure. If the pressure is measured or given to you in kilopascals, then the value for R is 8.31. And look at the units. It's a big funky unit composed of 4 separate measurements. The ideal gas constant units are liters times pressure of some value, in this case kilopascals, over kelvins, the units for temperature always, and moles. And what we have in those 4 units is a combination of all of the units in the measurements, the different ways that we measure gases. Again, reminding you that when we use this or any other gas law, your temperatures have to be in kelvins. And we just have to pick the correct value for the ideal gas constant for R that matches the units that we have for pressure. And again, you don't need to memorize these. I'll let you know. So what's the big whoopee about the ideal gas law? We have that handy-dandy combined gas law that has P1 V1 over T1 equals P2 T2 over, whoa, that's a V. P2 V2 over T2. That is nice penmanship. That is really nice. Look at that. See, I can erase. That's a P2. I have to turn my pen back on. P2 V2 over T2. So we had the combined gas law already that has pressure, volume, and temperature measurements in it, but we don't know about moles, and moles are essential if we're going to do stoichiometry, if we have chemical processes, chemical reactions taking place. And so the ideal gas law combines the values, all three of the values from the different gas laws that we've studied with moles, and gives us a way to get moles into our calculations. The ideal gas law that I remember, at least the form of it that is always in my head, is PV equals nRT. And I'm going to write that up here. Pressure times volume is equal to N, the number of moles, times R, the gas constant, times T, the temperature in kelvins. So this is the form for the ideal gas law. Pressure times volume equals moles times the constant times temperature. And you can remember that single form of the equation, or if you are one of the people who has a difficult time manipulating algebraic expressions, and there are plenty of those folks out there in the world, then you may want to go ahead and pre-arrange the formula to isolate the different variables so that you sort of have that in your head, what those look like. So if I wanted to calculate moles, to isolate the end, I have to divide both sides by RT, and so that's what the expression would look like if I wanted to figure out moles, which is what the questions are going to be asking about on this slide. If you wanted to isolate any other variable, though, you can just rearrange the equation. If you needed to calculate temperature, for example, then you would have to divide both sides by the number of moles and the gas constant. So it would wind up being PV over NR. And again, you can manipulate as much as you need to, but if you don't have problems doing that, then just wait and remember one form, PV equals nRT, and you're good to go. There's a bad joke that goes with PV equals nRT, and if you ask me about it in class, I'll tell you the really bad joke. Anyway, so if we look at problem number 1, this is a good example of how helpful the ideal gas law can be. It says a rigid container holds 685 liters of gas, and the gas is helium. That's going to become important in a minute. So the 685 liters, we've got our volume, and we have the temperature, 621 Kelvin. Thank you very much for putting it in Kelvin already. We don't have to convert from Celsius. The pressure of the gas, 1.89 times 10 to the third kPa, kilopascals. So we got our P, we got our T, we got our V. Hey, things are looking good. We got this guy, we got this guy, we got this guy, and this is given, the gas constant, so we ought to be able to calculate moles. Ah, good. And then the question says, how many grams? Grams is not in the ideal gas law equation. Grams is not there, but moles is, and with moles we can get grams, right? We can use the molar mass of helium to get the grams. And it shows the importance of this equation. If we can figure out grams, or if we can figure out moles, we can plug into the gas law equation and get temperature, volume, or pressure. Or if we know the temperature, volume, and pressure, we can figure out moles, which would enable us to get grams, another important measurement. So setting this one up, we would do the N equals PV over RT. We've got the pressure, 1,890 kPa, times the volume of the container, 685 liters. We're going to divide that by the gas constant, which, because we have units for pressure, kPa, our gas constant needs to be 8.31. And our final value, the temperature given already in Kelvin, 621. And we plug those numbers into our calculator and go, remembering that when you hit that divide button, you also use the parentheses so that you keep your order of operations straight and get the correct answer. I'm not going to plug those numbers in, but we're going to find out moles when we do that calculation, and then we're going to use those mole values to use that mole value to calculate the grams of helium. And whoa, I'm having a little trouble with my clicker. Thank you very much. So see if you can do the second question on your own. Careful there, the temperature's in Celsius, but otherwise it's a pretty straightforward setup to get moles using the equation. All right, a couple of little sort of aside things here, some useful variations of our ideal gas law equation. The first is to calculate a molar mass using PV equals nRT. And one of the things that we may want to do, and we're actually going to do a lab, I hope, that will involve this, is to determine the molar mass of a gas. And it's possible to do that in different ways, but one of the ways is to use PV equals nRT as a means to determine the number of moles and therefore the molar mass. Now you can rearrange PV equals nRT algebraically, the way it's shown in the slide here, to give this formula that's given on the bottom. And if you want to memorize that equation, by all means, go for it. You can memorize that equation and it will help you determine the molar mass if you're given one of these questions. But you don't have to memorize that equation. All you need is PV equals nRT, because if you know this equation, you can calculate moles. And if you know the number of moles, a molar mass is the grams per mole. So if we can calculate the moles, and they've given me grams in the problem, which you would need to use this other formula anyway, then you can get your molar mass by grams over moles, getting the moles from the use of the ideal gas law equation. So you can remember that formula if you want, but I don't necessarily think it's all that important. What is important, and you'll find several questions on your test that relate to this idea, is the relationship between density and gases. The density is the mass over volume, and for gases the units are virtually always going to be grams per liter. Gases are not very dense, so grams, a relatively light mass per volume of a liter, a decent sized volume. And if we know the density, usually when we're given a density in a question, for a gas it may be something like 1.49 grams per liter. And we write out this unit grams per liter and we sort of forget about it. But when we have grams per liter, just like the compound units that I've pointed out to you guys all year long, we have two measurements. We have the number of grams and we have the number of liters. And that means that we have two values that are potentially going to help us solve a problem using the ideal gas law. Because we have liters, we can plug that in for V. And because we have grams, well, if we know the molar mass of that substance, if we know the formula, of that substance. We can use those grams to get moles, and now we have two of our important values in the PV equals nRT expression. We can use that to calculate a lot of unknowns. So using density is important in lots of gas and gas law applications. So look for some of the example problems that will work in class next time and on your preview to see how those are going to manifest themselves in the questions you're going to have to answer. Here's an example, and it's all worked out for you, so I'm just going to pause. Let you pause the video and take a look at this, but I'm moving on. The last idea is real gases versus ideal gases. And this is a lot to do about really kind of a small idea, but it's an important idea. The ideal gas laws and the gas laws that we've already covered, Boyle's law and Charles's law, etc., those laws are all assuming that gases behave the way we say that gases behave. And that is that the particles are very far apart, that they don't interact with each other, and that the particles are so far apart and so small that they take up no volume in their containers. In other words, the entire volume in a container of gas is empty space. The molecules themselves don't take up any space. Well, that's an ideal gas, and that gases more or less behave that way is true. And that assumption is the basis of all of the gas law problems that we've been working, but it's also a false assumption. Particles don't have any volume. Atoms and molecules don't take up any space. Well, that's wrong. And we've also said that they don't interact with each other, that the molecules don't attract or repel each other, and that's also wrong. They do. Now, they are so far apart that they take up a very, very small percentage of the volume of the gas. So, the particles, that is. So, if we assume that they take up zero volume in their containers, we're only slightly wrong, and such a small percentage wrong that it doesn't affect our calculations very much at all. And the same thing is true. The attractive forces of the particles would also affect some of our calculation if the molecules had strong attractions or repulsions for each other. Well, they do have attractions. All particles have the potential to attract or repel each other, depending on their charges. But the attractions between gas particles are weak. That's what makes them a gas. And so when they're flying around in their containers at crazy fast speeds, and their attractions are very, very weak for each other, we can essentially say that the attractions are nothing. Well, gases are not ideal. They are not perfectly zero volume and perfectly no intermolecular forces. But when we have a sample of gas the way we normally experience gases, relatively warm temperatures like the temperature of the air or warmer, relatively low pressures, atmospheric pressure or lower, or maybe a little bit higher, but not crazy high. Under those conditions, the molecules obey the ideal gas law conditions enough that the ideal gas laws are more or less true, and our calculations are fine. So, again, if we have a gas that looks like this, are these particles taking up a very large proportion of the space? No. And are they going to interact with each other when they're moving around super fast? No, not really. So we can ignore those ideas. That's true at low pressures and high temperatures. But those conditions aren't always true. There are conditions where gas molecules take up a large proportion of the volume of a container, and there are conditions where the molecules do interact with each other in a significant way. If particles weren't attracted to each other, well, there wouldn't be anything other than gases, would there be? So what are those conditions? Well, it's the opposite of what I just mentioned. If the temperature is very, very low, then the particles are moving so slowly that the intermolecular forces now have a chance to have an effect. If the particles are flying by each other at a super fast speed, a weak attraction is not going to have very much of an effect. But if the particles are moving super slow at a super cold temperature, now a weak attraction might be enough to pull two molecules close to each other. Likewise, if they are under very high pressure, we are squeezing the particles closer and closer to each other. Now the distance between the molecules is very short, and the intermolecular forces are going to be more important. And obviously, when the particles are all crammed close together like this, they are now taking up a much, much greater proportion of the volume of the container. The empty spaces in the light blue here are just about equal to the spaces taken up by the dark gas molecules. And so now that assumption that the particles aren't taking up a significant volume of the container is blatantly false. And when we do calculations using the ideal gas law or other gas law equations, when we do those calculations under very low temperature or very high pressure situations, or a combination, our calculations wind up being very different from the actual values that we measure when we do those experiments. So we know that the ideal gas law works great when the gases are relatively warm, relatively low pressure, but those ideas break down when gases start behaving like real substances. So there's a summary of what we just said, and that's enough. We'll see you guys soon.